Hello and welcome to the third lesson in our series of learning general relativity. Have you ever wondered how the universe truly operates from the motion of stars and planets to the subtle curvature of space-time itself? Well, in order to know that, in this video we will unravel some of the basic principles of relativity and will explore the hidden symmetry in nature that links motion, forces, and the very fabric of space-time. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the third course on learning general relativity. Well, in order to learn what we call as the subtle fabric of space-time and the motion and forces, first we will start with this, which is called the principle of relativity, and this is something which we have actually touched a little bit in the earlier video, but we will look more onto that. Now, Galileo's philosophy emphasized observation, experimentation, and reason as the foundation of scientific inquiry, rejecting blind adherence to tradition or authority. Now, what we see here is that the persistence of the motion, or what we call inertia, as discovered by Galileo, leads to the impossibility of discerning the state of motion. Now, in the thought experiment that we saw in the last video of the stone and the boat, Galileo reveals that the persistence of the motion implies that experiment has the same result. Either the boat is moored or sailing. In both cases, the stone falls at the foot of the mast. Now, in classical mechanics, so we frame this kind of a principle, which we call as the principle of relativity, or the fundamental principle, that these same fundamental laws of physics are fulfilled in all inertial frames. Now, although it sounds very rudimentary, but we will see that this would take us into the principles of equivalence principle and later into Einstein's field equation. So from the boat experiment that we just saw over here, we deduce this, that the same fundamental laws of physics are fulfilled in all inertial frames. Now, in classical mechanics, Newton proposed the existence of absolute space, which serves as a fixed background, universal background, against which all types of motion occurs. In this frame, there exists what is called a privileged reference frame or reference systems, which is called inertial frames, and these are defined as frames of reference where Newton's law of motion, especially the first law of inertia, hold true without any external corrections. So this is something which comes from the Galileo's principle and then as framed by Isaac Newton. However, the same fundamental laws are fulfilled in all inertial frames remains true. We also saw from the boat experiment, what we can say is that the inability to detect absolute motion. So the person who is performing the experiment cannot detect the absolute state of motion of their inertial frame by internal experiments, because the laws of physics remain the same regardless of the frame's uniform motion. From there we came to know what is called absolute space. The concept of absolute space provides a theoretical background defining inertial frames. However, the principle of relativity that we saw negates the idea of an absolute state of motion. The equivalence principle, or I would say the equivalence of the inertial frames, required that the laws of physics behave properly under coordinate transformation. So in our first approach in the last video, we saw the principle of relativity. We combined that, the principle of inertia, with the Galileo's additional theorem, which you can see on the left hand side of the equation of velocities, in order to state that if the principle of inertia is valid in a given reference system, then it will be obviously valid in other systems translating with constant velocity relative to the first one. So from here, what we can till now understand is that we combined the Galileo's addition theorem along with that the principle of inertia, and which states that if it is valid in one frame of reference, it will be definitely valid from other frames of reference. Now from here there are certain, I would say, important inferences or some important I would say conclusion that comes across. The first is this one, which we call inertial frames of reference, that the same fundamental laws of physics are applied in all inertial frames of reference, those that move uniformly and rectilinearly with respect to one another. In the thought experiment illustrates the principle of relativity, that experiments cannot distinguish between a moving and a stationary inertial frame. We also see that the fundamental physical laws, for example, conservation of laws of equations of motion, etc., apply identically in all inertial frames, which underpins what is the principle of relativity. From here, what we find is that the principle of relativity ensures that the fundamental laws, example Newton's laws or even classical electromagnetism and eventually Einstein's field equation, take the same form in all inertial frames. And absolute space may conceptually exist as theoretical idea, but obviously it is not undetectable. This is an observational consequence. So no experiment within an inertial frame can reveal whether it is at rest, moving, or how fast it is moving relative to absolute space. From here we find this one, that the this principle underpins modern physics, ensuring that physical laws remain invariant, and that is basically what we generally target in terms of framing a kind of a proper or a foundational physical law. As far as the Galileo's law of transformation, I would say the addition theorem of velocities is concerned. To demonstrate this, differentiating the velocity transformation with respect to time, what we see here is that u prime is the velocity in the primed or the moving frame, u is the velocity of the unprimed or ordinary frame or stationary frame, and capital V is the velocity, relative velocity between two inertial frames. So taking the time derivative in both sides of the velocity transformation leads to this kind of an equation, and from here we get three things very important. This one accelerated in the primed frame, this one is accelerated in the non-prime frame, and this one is the time derivative of the relative velocity v. Now why I am stating this is simple calculus differentiating with respect to time is that it actually leads to something very foundational, something very simple, but something very important, which underpins the entire concept of relativity as a whole. So from here, if we move from to here, what we get is that we keep this value as the same. So dv by dt equals to 0. Now substituting the values further, we get a prime equals to a. And this means that it shows that the acceleration remains invariant under Galilean transformation, that is same in all reference frames. Now hold on, this is under Galilean transformation, we can see that acceleration remains invariant, but in Einstein's general theory of relativity we will see that a moving object experiences at all no acceleration. These two are different. One is acceleration invariant, another is no acceleration, but however it actually crops up from here. So that is why I have said that why it is so important, and we will next see that the importance of acceleration remaining invariant shows few important concepts in physics. First of all, it says that the second law of Newton, that is F equals to ma, it holds true in all inertial frames. Now if this holds true in all inertial frames, we will also see that under weak field approximation, this F equals to ma will lead to the geodesic equation. Now because I would say in other hand, the child is bearing the gene of the mother. So in one way, if the mother has got certain features, obviously the child will have. So if F equals to ma holds true in all inertial frames, we will also see that how the geodesic equation, which is the child evolving from the mother, will have the kind of the same kind of characteristics. A prime equals to a also shows that the consistency of Newtonian mechanics across all inertial frames, and let us not forget that Newton's second law and the laws of motion actually gave rise to relativity, so again it will carry the same characteristics. The fundamental laws of physics in terms of mechanics are the same in all inertial frames, and this would lead to a kind of a precursor to Einstein's special theory of relativity, which is the foundation stone for general relativity, and we will see that which generalizes the idea of invariance, that is Galilean transformation, are later replaced by Lorentz transformation relativistic physics. Now, as soon as the Galilean transformation are trying to be replaced by Lorentz transformation, there will be problems, there will be incumbents that it is not framing the equations in terms when it is moving close to the speed of light. Those things will come. But a prime equals to a, which is that the acceleration is invariant under Galilean transformation, will lead to special relativity, which will eventually lead to general theory of relativity. So this is what is called the principle of relativity, coming from Galileo, then to Isaac Newton, and further expanded by Albert Einstein. Now this is the point where we now need to have two very important concepts of physics. I would say rather two important concepts of mechanics which will be applied. That is, what is a dynamical law and what is an interaction law. Now these terms seems to be known, but in terms of relativity, these things will slowly evolve into a beautiful new, I would say, theoretical model. So first let us understand what is a dynamical law. Now, when we say dynamical law, I mean to say that the laws in physics are fundamental principles that describe how physical systems evolve over time. Now, this has got great many implications, but let us understand that how a system is evolving. I will show you some very easy, I would say, demonstrations on that. So these laws are actually expressed as equations, often involving forces, motion, energy, etc. Now let us imagine this x and y axis, whatever be you can imagine in the x axis, however the y axis will tell the time. Now let us imagine this to be a system, any kind of a system. It can be a thermodynamical system, it can be a quantum system. Let us imagine that this system behaves so in time t equals to 1. Now when we go to time t equals to 2, the system evolves. Now how it evolves, what are the wave functions or mechanics, that let us leave apart. It evolves, and then in time t equals to 4 it evolves. So it shows that a system over time, how it evolves. Now there are, say for example, there are two particles, this one which is traveling, that means it will slowly evolve and reach over here. So that is also kind of a time evolution. The system is evolving. So from here what we can say that how a physical system evolves based on whatever is acting on it, forces, motion, energy, fields, whatsoever. So we say that Newton's laws of motions governing motion of objects under the influence of forces. Maxwell's equations are all dynamic because it describes the behavior of electric and magnetic fields. Schrodinger's equation, obviously it is a time evolution of quantum states. It shows how a system evolves over time. And obviously Einstein's field equations, which describes the matter and energy influence on the curvature of space-time. So this is how a system is evolving. A particle is moving, a quantum state is evolving, electromagnetism is behaving in a different way. So this is called dynamical laws. It is called how a system is evolving. Now, if you talk of interaction laws, then we say that interaction laws in physics describe how entities, for example, particles, fields, objects, whatever, influence each other, and these laws are defined by the fundamental forces. That means how things are interacting with each other. Now, if you go to this one, you will see this is more of a macroscopic phenomena. The system is evolving over the factors like forces, etc. But this is most of a microscopic, I would say not microscopic, but a little bit micromanagement phenomena, where the things are actually happening with each other and they're interacting. Say for example, we have got gravitational interaction. That means how the attraction between masses, Newton's law of gravity or general relativity, something like that. Electromagnetic interaction governs the interaction between charged particles. You can say Coulomb's law or Maxwell's law. Strong nuclear force binds protons and nucleus in the nucleus via the strong force, and weak nuclear force, which is responsible for the process like beta decay of particles. So from here we can say that these laws actually explain how the forces operate and propagate, which shapes the structure of the dynamics of the universe or the system. So the basic difference between the two is that the dynamical law, it shows how a system evolves over time. Interaction laws explain how entities or particles influence each other through different kinds of interactions. Now, I will now show you why this is important in terms of understanding relativity. So we move on to the next part of the video, where I would like to show you this kind of a very simple animation. So this is the dynamical law, and describes how objects, when acted upon, and it behaves like a force. So we can say the dynamical law is F equals to ma. and when the force, if this is an object, and how the force is acting. So what happens to an object when the force is known, how it is acting? So this is the dynamical law. If we take kind of an interaction, for example, things are interacting with each other, this animation gives you a kind of an understanding. So we get something that these laws specify the nature of forces acting. Now if you use the Newton's law of gravitation, this F would be telling the interaction how to calculate the force. We get the similar thing in electrostatic Coulomb's law, and we get the same in Hooke's law, how the spring attached to it, how they behave, Fs equal to Kx. Now, this dynamical law, we will first take the dynamical law. Overall, what I told you is a macroeconomic way in how things actually evolve. It takes a different kind of a shape in general theory of relativity. So, if we take both the sides, let us see dynamical law and general and interaction law. So, this F equals to ma, and this one, if you take the Newton's law of gravitation, these are actually complementary. So, if you say the dynamical law guides the interaction law, and interaction law actually shapes the dynamical law. In the same way, how general theory of relativity is, you will see Einstein's field equation, left hand side and right hand side actually evolves. The left hand side is more or less dynamic in nature, which shows the curvature of space. I will explain to you later. Yeah. So from here, the dynamical law provides a framework for understanding motion, and interaction law is more of the detailing of how the forces play. But what we get is something beautiful, because together they provide a complete structure for predicting and understanding the motion of particles. Now these two laws are modified in a very crucial and a different way, as we will see in general relativity. The overall idea, the overall philosophy will remain the same, but things will be a little bit different in terms of understanding general theory of relativity. Let us look at a very important part of our discussion into this part of the video. Considering the dynamical law of Newtonian mechanics, if I take F equals to ma, so we know that how physical systems evolved, and in general relativity also it shows how a physical system evolved. As here it shows how particles move based on the forces, motion, etc. In general relativity is also shows that how a particle is moving along a geodesic. So that is what is called the geodesics. Now if I take a kind of a positive curvature, a sphere, and I place a particle over here, and I try to map the geodesics, it will move something like this. And it will land over here. So this will be the equation which is guiding the dynamical law. I mean to say, from Newtonian mechanics, how the system is evolving, how the particle is moving, this is being guided. And remember that when we showed this kind of an animation, it actually follows what is called the straightest possible path. It is not taking a curvature. It is just because of the curved space-time, it seems that the particle is taking a curved space, but it is moving in the straightest possible paths. So, in general relativity, if an object is moving solely under the influence of gravity, it experiences no proper acceleration. As I told right at the beginning of the video, A prime equals to A under Galileo gives a hint that acceleration is invariant under Galilean transformation. Here Einstein is telling that when it is moving, free-falling particle under geodesics actually experiences what is called a no acceleration. Now this actually shows how the dynamical law gives a hint to frame a better complex theory into geodesics, which is the general theory of relativity. But remember, the dynamical law, the essence, the philosophy remains the same. We take the same F equals to ma in a very simple manner, and in this part of the video I will just show you that how we can write it in a component form. You might say that we all know this, but this will actually act as a kind of a link to the other concepts of relativity. So if I take F equals to ma as into components, so what we know that force is basically a vector. And also we know A as acceleration vector, and M obviously will be scalar quantity. So force F, suppose the total force acting on the components are actually X, Y and Z. These are the, three axes in a three-dimension manner. Acceleration can also be plotted as X, Y, Z. So we are taking force acting upon the objects. It has got three components, Fx, Fy and Fz. So obviously it will be Fxi, Fyj and Fzk, where I being the unit vector. That is why it has got a hat. In the same way we write acceleration, Axi, Axy and Axj and Xk, Ijk. So for what we do is that since F equals to ma, we try to apply to each components independently, and we can express the force in each direction as follows. So what it would be: Fx equal to max, Fz equal to maz, and Fy equal to may, considering x, y, and z, these are the axes. So this is how, in the way we write it. Now, if we put all those equations in a kind of a vector equation, we get obviously this. And if we can expand this simple, we will get something like this. So if this is an object and force is acting up and on it, we can describe by 3 component equations, which is this, and this. Now, what we are going to do is that this is the F equals to ma. Remember, this is a dynamical law, which is the mother, and now we will see how the child is being born. So we will now look into what is called from F equals to ma, because it shows a system's evolution, and geodesic equation also shows a system's evolution. We will see how F equals to ma can be written in the form of geodesic equation. This is not a very hardcore deduction or a derivation, but just to give you an essence. Now, we know that acceleration a, which is a vector, is the rate of change of velocity with respect to time. So we can obviously write as a equals to dv by dt, and velocity v itself is the rate of change of position r with respect to time, which we can write as v equals to dr by dt. Therefore, acceleration a can also be expressed as a second derivative of position with respect to time, which is this one, a equals to d square r by dt square. And if we substitute the acceleration is into F equals to ma, then what we get is this one, a equals to d square r by dt square. And this is, remember, it is a differential equation, and this shows that F is the force, m is the mass, position is the r as it changes over time. Now, this equation, F equals to m d square r by dt square, just keep it in mind, this will be something very similar, analogous to what we called the geodesic equation. Although the geodesic equation contains a lot of parameters, but at least you can get how the child is being born. Right, so that is how from the mother the child is being born. And so F being the force, mass m, position r as it changes over time, r being the radial vector, which we have dealt in the earlier video. So from here, F equals to ma, we deduce this one, right? And from here we can write, this is what is called the geodesic equation. Now see how the child is being born, which is a much more complicated equation than his or her mother, but it carries the similarity with that of the mother. So here you can see d square x mu by d tau square. Isn't it something which is similar to the acceleration formula, which is this one? Here you get a second derivative, here you get a second derivative, here you get a second derivative of time t, here also you get a second derivative of time tau, which is a proper time. We will deal with that later. So this carries a resemblance as the mother and the child. Now this one, this one, this one, and this one, same kind of characteristics. And this is r, this radial vector r is being replaced by x mu, which we will deal later. This is called the space-time index. Now, so this is actually representing the coordinates of the objects in space-time. However, this part of the equation, this is something a little bit complicated, which is called Christoffel symbol. Now, Christoffel symbol again has first kind, second kind, which I will explain later, but it encodes the curvature of space-time. And this tau is called the proper time. So remember, this now becomes very important, that the geodesic equation is a force-free version of F equals to ma. In F equals to ma, we get a force. But geodesic equation is a force-free version, and what it describes how objects move through curved space-time, although it takes the straightest possible path, guided only by the geometry of space-time, which is a manifestation of the gravity, what we call as gravity. So it resembles the same characteristic as that of its mother, the mother and the child. So it will have the same characteristics as the second derivative of time, which we deduced from F equals to ma. Right, so from here what we see that the interaction law in Newtonian mechanics is influencing the fields, etc. And in Newtonian mechanics, Newton's law of gravitation describes how the gravitational force interact. So this equation now, now we are talking of the interaction law. The first one we have already done. That is what is the dynamical law. So this will be replaced by either this or this. I mean, this is the first one is expanded form into what is called the Einstein field equation. Now, this derivation is not as simple as the geodesic part. It will require a few more videos, but this is what is the Newtonian law or the interaction law. Now it starts interacting with the Einstein field equation. Now, once I say that this is an interaction law, definitely I have to prove, isn't it, that how things are interacting. Now I will show in the next part of the video that this law, how we call it as an interaction law. First of all those mu nu, they are basically a kind of a 4x4 matrix, or we can say kind of encodes the nature of space-time. So it is a 16 set of partial nonlinear differential equations, and the left hand side it measures the curvature of space-time. The right hand side now shows the energy and momentum of matter. Now, because it is measuring the curvature, what it is showing the evolution of a system. And right side again is an interactive equation. Why? It is showing the interaction between energy, momentum, matter, density, etc. So from here we can get a kind of this kind of a diagram, which is very common in internet otherwise, that there is an element on the curvature of space-time and is creating a mass, a curvature. So here it comes, that interaction laws which describes the particles, fields or entities, here also it happens the same. Now here you can see first, which is called the stress energy momentum tensor. Isn't it interacting? Obviously it is interacting. It is interacting with matter and energy, etc. The second comes, which is called the metric tensor. Isn't it interacting? Yes, it is interacting with the causal structure of space-time. So this actually justifies the definition of interaction law by quantifying the reciprocal influence between matter, energy, etc. Now I am taking the equation as a whole, not the left and right, as a whole. I'm trying to say that this is basically coming from Newton's law of gravity, which is a kind of an interactive equation, whereas F equals to ma is more on the system evolution. Now, as I was talking that the child bears the resemblance of the mother or the father, etc., we will see that how it goes back to the child, and this happens under a situation which is called a weak field approximation. Weak field approximation and what is called the Poisson's equation. Now, first of all, before we move into Poisson's equation, I need to make you understand what is a weak field. Now, it's very simple. Now, weak field is basically a kind of a method which is used so that the equations are very simple. And we assume that the gravitational field is relatively weak, not very dense, and space-time is only slightly curved. So this approximation actually helps us to, study situation where the gravity is small, like the solar system or something like that. So the most important factor is that the space-time metric is not as curved, and it is more or less flat like the Minkowski metric. It looks like this. The gravitational potential, which we will see, which is the phi, is assumed to be much smaller than the speed of the light squared as near the planets and stars, and it looks something like this. Now this part, which is, you can see this h mu nu, I will come to this later in a different kind of a video. This h mu nu, if it is called linearized Einstein's equation, this h mu nu, if it is small, Einstein's equation is linearized and it shows something like this, where this box actually is a D'Alenbertian operator in flat space-time. We will look into that later. I'm not going into this equation. It will take some time. So what we can say from here is that the approximation is applied to non-relativistic, that it is slow, less curved, less than the speed of light, etc. And the space-time metric is also written in a non-perturbative or as a perturbation of Minkowski metric, which is more or less flat. So that n mu nu, which you can see on the left hand side, is the Minkowski metric flat space-time, and h mu nu is the small perturbation. It's a very small perturbation, less than equal to 1 or something, that represents deviation due to gravity. So what we can understand, that we are taking a very low approximation, perturbation is less, and that actually helps us in terms of understanding gravity or the equations. So applying this Newton's law of motion to an object would lead to this, which produces an acceleration, and we get something which is called this. This is actually what is called the Poisson's equation. Now note here what I'm trying to tell. The first thing is this Nabla squared. Now this is actually what is called the Laplacian operator. You can say that it is essentially what we can say. You can imagine it's something which varies with this phi. A kind of a measure of the curvature. That means how much the curvature is spread, or it is dense, or it is less dense. Something which the Laplacian operator approximately tells you. Now coming to this phi, which is very important, it represents the gravitational potential. It represents the gravitational potential in the sense that, remember, it is a scalar function. So the gravitational field in terms of potential per unit mass. So the gravitational force can be derived from this potential with the force acting in the direction or decreasing on whatsoever. Then we come to what is this called this 4 pi. Now this you already know is because of the spherical symmetry of Gauss's law, because it arises when we are integrating over a spherical surface area, because the area is 4 pi r square, so it deduces from there. G and rho, G is already defined, I have not mentioned that gravitational constant, and this one is the mass density. Mass density is, that means how much mass is contained within a given volume. So if the mass density is greater than 0, phi will more curve, and a higher value of pi will indicate more mass. So the overall what we can see from here is that the higher values of rho on the extreme right hand side, the higher values of rho actually indicates which region and which area has more mass will create a stronger gravitational field. So overall what we can say that the equation tells us that the Laplacian of the gravitational potential phi is proportional to the mass density. In regions where rho is greater than 0, the phi will curve more. Now taking this ahead, what we can tell a little bit more is that this is in summary Poisson's equation. So it actually tells you that the gravitational field, the acceleration A, is experienced by a mass which is related to the force per unit mass. So the acceleration is given by the gradient of the potential, which is this one. Now I will soon explain you why is this minus coming. First let us understand that the gravitational field, the acceleration A experienced by a mass, is directly related to the force per unit mass acting on it. If the gravitational acceleration always points towards the force of gravity in the direction where the potential decreases more rapidly. Okay, let me give you an analogy. If, say, for example, the person, this is again an analogy, remember this is not correct. If, for example, the gravitational acceleration will always point towards the source of gravity. So if it is moving up, I mean to say if it is moving upwards, then it is pointing in the direction of increasing potential. The acceleration will also point in the increasing potential. If you get some kind of an analogy like this, then acceleration points downhill. The potential landscape, it will point towards negative. So the A equals to minus nabla phi means the right hand side. It means that the object accelerates in the direction where the potential decreases more steeply. Remember, it is a gradient. So that is why I told that the acceleration is given by the gradient of the potential. And the left hand side, the positive potential, is basically in the case the acceleration will also point in the positive in the direction of the increasing potential, meaning what? The object will move towards regions of higher potential. Now, in order to make things a little bit easier, what I would like to show you is this. It means that the acceleration experienced by an object in gravitational field is determined how quickly and in which direction it is moving. So let us imagine this to be an energy landscape, and this is a landscape, and this is where it's like a map in a gravitational energy space. So if the hill is up, it will move in this. If the hill is down, it will create a lower potential. So it is like a map. So what I'm trying to make out of this is that the gravitational potential is a map of gravitational energy in space. So think of it as a landscape. Things will become easier. Peaks represent higher potential and valleys represents lower potential. Simple. And this one, this nabla phi actually represents the rate and direction of the steepest increase in potential. That means what? The gradient nabla phi represents the rate and direction of the steep. That means in terms of landscape analogy, the gradient points uphill, showing where the potential rises more sharply. So the relationship actually tells us that the stronger the change of the gradient in gravitational potential at a point, the greater the gravitational acceleration at that point. It also explains that why gravitational force and thus acceleration is directed towards massive objects, as they create regions of low potential that pulls objects in. Now so this is the weak field approximation. As I told, the mother and the child analogy, or the father and the child analogy, where it goes back. So now in the weak field approximation, if you see the mother and the child concept, then we see from F equals to ma, I mean to say the child goes back to the mother. So the geodesic equation crops back to F equals to ma, and also under weak field approximation, this would go back to this, and F equals to ma is being invented as Einstein as geodesic equation. Similar to this mother and child analogy, this Einstein field equation, the mother is the Einstein law of gravity, Newton's law of gravity, sorry. And this is actually the child, so the child will come back under weak field approximation as this. So we will take a pause in today's third video, where I try to explain you all those concepts related to weak field approximation, how the geodesic equation, most importantly the concept of dynamical law, interaction laws, and how things actually evolve starting from Newton, Galileo, and then to Albert Einstein. Thank you very much for taking your time to watch this video. If you really liked the video, please feel free to comment and let me know reactions. Do not forget to subscribe and click on the bell icon to get all the notification from Physics for Students. This is my email ID, which you can write to, and you can follow my other channel exclusive to Einstein General Theory of Relativity. You can also follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Physics for Students will be back and continue with the courses which I have started. Thank you very much, and see you soon in the next video, and may the good Lord be with you.